Are you able to see the recordings? Have anybody checked?
Yes, yes.
Yes, it's talking.
Good. Great. Okay. All right. So what is modeling? Can somebody describe what is modeling and why do we need it for control? So we talked about the control, what it is and why we need it. Now we're talking about modeling. So how does that relate to it? I mean, you can just use your own words, even if the answer is not correct. It's fine. Yes.
Modeling is basically a set of equations that describes the system that we are trying to show.
Mm-hmm. Why do we need it for control?
We need it in the design, so for designing the control system.
Mm-hmm. Can you elaborate more?
It's basically like a mathematical equations that we have, so we can control our control system.
Exactly. So a model describes what the system, how the system behaves. And if I want to control it and make it behave in a certain way, I need to understand its mathematical model. So once I have a mathematical model describing the system dynamics, how things will behave in time and how do the variables relate to each other, then I can design a controller that gives me the performance I need. Okay, if that is feasible. So for this part, we'll talk about modeling of mechanical systems, and then we'll talk about modeling electrical systems. And then we'll start talking about differential equations and their solutions and the Laplace transform. The reason we care about differential equations and control is that usually we care about dynamics. Dynamics are things that can vary with time, and differential equations is one way of capturing dynamics. So the objective here is to derive mathematical models of simple translational mechanical systems. So the first step in the design is really the modeling step. And one thing that I want to mention is that modeling can be done in a physics-based approach, like what we do in this course, but it can also be done in other means. You can use machine learning, you can use whatever you want to use. There is what's called system ID, system identification. So really what you do is that you don't know how to model this. So this is applicable for, let's say, social systems. You don't know the model. So you give it input data and you observe the output and you try to build the relationships experimentally. So for mechanical systems, we have displacement. Really, it's a vector. It's not like distance in which it does not have a direction. Displacement has a direction. So we mentioned last time that, for example, if you move from this point to this point, the displacement is 1. Why? Because you're just 1 to the right, but the distance traveled is 5. So the distance, because it does not capture the direction, it has a different value than the displacement sometimes. But if I just move in one straight line to the right as 3, then the displacement is 3 and also the distance is 3. However, the displacement will give me more information about the system because it tells me the direction of that movement from one point to another. All right, so with that, you have the derivative of the displacement that captures the velocity. Velocity, again, is the same as speed, but with the direction. So it's a vector. So velocity is really the rate of change of the displacement. And you can also have an acceleration, which is the rate of change of the velocity. And that is the double derivative of the displacement. So all of these things are things you saw in physics 101. But you can consider this as a quick refresher. We also need to have a reference direction, which is the direction that we consider to be the positive. so that anything in the opposite direction to that is considered negative. We also discussed the following example, f being cosine of half t, and we identified the range in which the direction is the same as the reference direction for t, and the range in which it is in the opposite direction. So basically 0.5 t is between 0 and 2 pi, right? So for the first and the fourth quadrant, you have the range that gives you something in the same direction as the reference direction, and in the other quadrants it's opposite. So we captured that, but here because you're multiplying by 0.5, you need to multiply by 2 in order to get the range in terms of t. Okay? Any questions so far? All right. So we said also there is what we call a reference position. This is the position that we call 0. And then anything else we need to measure, we measure it a reference to that position. For example, x of t here represents the distance from the left side of the body to a fixed wall. So x being 0 is selected as the equilibrium position, which is here, with no external forces applied. So what does x minus 3 mean? Here it means that you are 3 meters away from the equilibrium in the opposite direction to the reference direction. So you are, let's say, here. Then again, similar to the distance, we have a reference direction. So we take something to a direction to be a positive, and then the opposite to it is negative. Usually we take that the direction of the movement. So if I have the force being minus 5 newtons here, it means that it is to the opposite side of the reference direction. So if the reference is to the right, then minus 5 is really to the left. All right, so what we do here for modeling mechanical systems, we have what's called elements. They capture some mechanical phenomena. And then we study the relationships between these phenomena. And then based on that, we build a mathematical model in which we want to control. For example, we use some physical devices that represent one or more idealized elements with some approximations. We use the mass, friction, and stiffness, and we'll talk about what each term here means in the context of this course. So for the mass, really, it's the quantity of the matter in kilograms. Nothing new here. And the sum of forces applied to a body is equal to the rate of change of the momentum. So the force is really the rate of change of mv, where m is the mass, v is the velocity. However, the mass here, we don't consider it to be a function of time, so we can take it outside the derivative. But if the mass changes with time, then you do not do that. You have to consider the rate of change of mv. Okay? Have you seen a mass that varies with time in any course?
I don't think so.
Okay. Yeah, but you might have that sometimes. So, I mean, it's not something we usually cover. So we'll just take it as a constant. All right. Then we have friction between surfaces. So we use these lines to indicate friction, and we use the wheels to indicate a frictionless area. So when a body moves on a surface, a friction force is acting in the opposite direction of the motion. Friction can be linear or nonlinear. Linear friction is called the viscous friction, which is proportional to the difference in velocities of two objects. I mean, here we have a linear approximation. So really the friction is B, some coefficient, or the slope of this relationship, delta V. This is the difference in velocities between two objects. So this is the friction force, and we will talk about it in more detail in this lecture, inshallah. So what is the unit of B? B is a coefficient, right? It's a constant. What is its unit? All right, what is the unit of the force? Yes, Mazen.
Newton second per time, Newton second per meter.
This is the unit of what exactly?
B.
Okay, you're saying it's newtons second per meter, right? So how do you know that?
Just by dividing both sides by delta V.
Exactly. So the unit of B is the same as the unit of F over delta V, which is newtons over meter per second. Take that here to the denominator, and you have Newton second. That is correct. All right. So we said this is how we represent friction. We represent it as B multiplied by the proportional speed, the proportional velocity. And then we have stiffness elements, which we capture as a spring. So these stiffness elements are mechanical elements that change shape when subjected to a force. Okay. And we use a spring to represent stiffness. I mean, you don't need a spring everywhere, but I mean, spring is something that captures this kind of phenomenon. So we use a linear spring, which is K delta X. So it's proportional to the delta X here is the proportional displacement, and K here is the stiffness element, the stiffness constant. Similarly, we can define the unit of it. It will be in newtons per meter. And here is, so we use that because once you apply a force, the length will change. So we use the linear stiffness element, and it's sufficient for the purpose of this class. All right. Then let's a little bit about the energy stored. So basically, stiffness elements store energy. And this is the formula of the potential energy it stores. It's just half K, which is the constant, delta X squared. And the mass stores energy too, in the form of kinetic and also potential energy. The potential energy is really mgh, mass multiplied by the gravitational force, constant multiplied by the height. And then the kinetic energy is just half mv squared. This is, again, you have seen all of these things in Physics 101. The idea here is just to give you a quick refresher before we move to the modeling aspect. We also use dampers to eliminate to represent friction, and they dissipate energy. So the next thing we want to talk about, maybe we dive a little bit deeper into the element laws and give you some representations of how we model them, the corresponding forces, so that once we have different elements connected to each other, we can build the entire relationship among them and have them with a complete model. For the mass, you have the inertial force. So it's really the mass multiplied by the acceleration, x double dot, or A. For the friction, it's just K, the constant, multiplied by delta x. Here in this case, delta x is x2 minus x1. So we take the one to the right as we are using this direction as the positive direction and subtract x. Okay. Similarly, we have b x dot for the damper. This is the velocity. And if you have two velocities, then really, if it's moving, if it's a moving object, then really, because we're taking the proportional velocity, so you have x2 prime minus x1 prime, or x2 dot minus x1 dot. So it's really just v2 minus v1. Yes, Muhammad.
معلش دكتور ايش هي بي مرة ثانية؟
B is the coefficient
حق ايش؟
for the friction.
اوكي يس.
It's a constant that you know, similar to K for the spring. Yes, Mazel.
Doctor, what is the meaning of the diagram on the left? I couldn't understand it.
Which diagram?
The one below.
So we represent friction. We represent friction as a damper. This is a damper. I mean, it's really a device that represents friction. So you can think of it as these lines. So we can use this or that. So again, the idea here is that you might not have friction exactly, but we have these devices to represent friction or something of a similar behavior that affects the velocity. It's called a damper. It's like when you have a spring, we draw it like this. You can think of this as this is a damper, and it really affects the proportional velocity.
Okay, thank you.
Other question? Okay. So we have, let's say, the laws we will use for every device or for every element. Now we want to build the relationships among these elements. So we use interconnection laws. These are really Newton's laws. So interconnection laws describe the way different elements are interacting. Okay. And then we have three important laws that will be covered here. We will use D'Alembert's law, and we will use the law of reaction force and the law of displacement. I mean, really, we mainly focus here. So what is D'Alembert's law? So first, what is Newton's second law? Newton's second law is that, so D'Alembert's law is really a restatement of Newton's second law. There is nothing new here. So what happens is that Newton's second law states that the sum of external forces is equal to the mass multiplied by the acceleration. Now, what if I consider this as an external force? So I can move it to the other side and give it a negative sign. So you will have minus m dv dt. If you do that, we call this the inertial force And if you sum all forces, then make them equal to 0, then it's called, this is D'Alembert's law. So it's really just a rearrangement of Newton's law. That's it, nothing new. The second law is really the law of reaction forces. So it's Newton's third law. So for any force of one element on another, there is a reaction force in the first element that equal in magnitude and opposite in direction. So if I have a spring, if I have a force to the right, then I have another force that is reacting to the left. This is really it, nothing new. Then we have the law for displacement. This states that if the ends of two different elements are connected, then both ends move at the same velocity, meaning that if I have a spring here, call it 1, and I have, let's say, another element, another spring, call it 2, and if they are connected at both ends, so for example, here I have a mass, call it M1, and here let's say I have another mass, call it M2. Notice that the ends are connected to the same object. Then, naturally, these two elements, 1 and 2, will move at the same velocity. This is it. This is what this means. There is nothing that is difficult to see here. It's just simple and intuitive. So here is an example. Since the dashpot and the spring, so this is this is a dashpot. It's something to it's a damping device, and the spring are both connected with the wall and the mass. The right ends of both elements have the same displacement x1. It's natural because they're connected to the same mass, so they must have the same displacement. This is it. Any questions so far? Okay. There is a restatement of that, saying that the algebraic sum of elongation of elements around any closed path is 0. So now we talked about element laws. We talked about the interconnection laws. So how do we build the model? So the system model is really obtained by combining the element laws and interaction laws. We will have examples to demonstrate this. So first, we need to plot what's called the free body diagram. So a free body diagram shows all forces acting on the mass. So you have a mass, and there are forces acting on it. So the free body diagram is just a representation of all forces on the mass or a junction point and their directions. So we draw the free body diagram for each mass or junction point that moves at a known velocity. So for example here, how to draw the free body diagram for this mass? Can somebody tell me how to draw that?
We have a force from the right, dragging it. Okay, so the spring is stretching, and because there is a wheel,
Okay.
and we have gravity.
Okay.
هذا اللي يحضرني حاليا.
Yeah, okay. So it's a horizontal movement. So we can, yes, Mazen.
I'm sorry, doctor, but what is the job of a dashboard? I don't understand it.
Okay, so it
Is it the
is
same thing?
so really so if we have, let's say, movements, and if we have friction and stiffness, okay, then these will affect both displacement and velocity. Do you agree?
Yes.
Okay. So for displacement, we use the spring to represent the objects that affect the displacement. So the spring is some representation of the stiffness in the system. Okay? It doesn't mean
Okay.
that I must have a spring. This only means that I use the spring because it's a good representation of stiffness elements in the mechanical system. So it has an opposite force
Okay.
affecting the displacement. Similarly, I use the dashpot to represent friction and anything else that affects the velocity of the system. And we represent it as a dashpot to capture damping. So these are the things that affect the friction. I mean, you can think of valves, you can think about these things.
But
So
is it equivalent if we remove it and draw the lines under the mass? Is it the same?
you draw the lines under what?
Under the mass instead of the wheels.
You want to draw the lines under the mass?
Yeah, that represents friction.
I see. Yeah. Okay, you can do that, but maybe also the location in which we draw it can affect. Maybe in this example it doesn't affect you, but maybe in other examples because of the location, because again you have a reference position and you need to also think about the displacements and all of these things, like the how far is it. So these are things that affect the system. So yeah, you can represent it in different ways, but really, the thing here that we want to emphasize is that there are different sources of forces. If it's a force that is affecting the system in a way that is acting in the opposite way of the displacement, like stiffness, we represent it as a spring. If it's something that is affecting the velocity, we represent it as a damper, as a dashpot. But you can also have friction. That's fine, yes.
Okay, thank you.
Okay. Again, these are idealized elements. All right, Faisal is saying we draw the directions of all forces that being applied to the object. Exactly. So we might have the object here, call it M, right? So what are the forces to the right?
Only the drag force.
You mean F of A?
Yes.
What are the forces to the left?
We have the spring and the damper.
Okay, so call this Fk. We have the damper, call this Fb. Is that it? Any other force that you can think about?
We have wheels. It's mean the fraction is ignored.
The friction here is ignored, okay.
Gravity.
What can you think of a new force that we need, not a new, but something we need to add because of Newton's law?
Gravity.
I mean, we just ignore gravity for horizontal movements.
Okay, we ignore it. Okay.
Yeah.
The friction.
So we captured B. It's for damping. Yes. Somebody raised his hand. Yes, Mazen.
If consider the resistance from the air.
Let's skip that. Let's just say all forces are being represented with some element like a damper or a dashpot. So let's ignore any other force that is not being drawn here. Yes, Faisal?
Doctor, for FK, shouldn't it be to the right since it's pushing the object to the right?
Is it? So this is the applied force. Imagine that you pull the object to the right by hand. Something you apply.
Okay.
Then the spring will act in the opposite direction.
Yes, I got it.
Okay, what does Newton's law say? So we said that Amber's law is really a statement of Newton's second law. What did Newton's second law say?
Mass by acceleration.
Well, yes, what did it say exactly? It said that the sum of all external forces is equal to the mass multiplied by the acceleration. Yes, Mazen, you wanted to say something? Okay. It said that the sum of all external forces is equal to the mass multiplied by the acceleration. So here we had an external force, the applied force to the right, and we have two external forces, the force due to the spring and the force due to the dashpot. We also need a third force to the left, which is ma, right, or x double dot. This is from Newton's second law. So do not forget that. This is the inertial, call it ma, or let's say fi. This is why I stopped here, because it's easy to forget about it because we don't see it presented in the diagram, but it's really important. It really captures the movement. So with that, we have four forces applied, four forces that govern the relationship of this, that govern the movement of this system. Okay, any questions? Yes, Mazen.
Yes, doctor, I don't understand the force of inertia. How is it applied in this system?
Okay, this is from Newton's second law. If I go back here, what does it say? It says that the sum of all external forces is equal to the mass multiplied by acceleration, right? Do you agree?
Yes.
Okay.
Yeah.
Now, if I move this to the other side, then it will be minus mass multiplied by acceleration, okay?
Okay.
All right. Now, let me go back to this diagram, the one we just had. What are the forces that are external to the system?
The spring, the dashpot, and the applied force.
Okay, so
As
yeah, because this is to the right, I can just put it to the left and call it, let's say, minus FA, right?
Yeah.
So if I want to use Newton's second law and ignore Fi, which is the inertial force, Fi is really the mass multiplied by the acceleration. If I want to ignore it, is the model complete?
No. It will be missing.
So yeah, so we have to include it in our discussion. It's going to the left, so that captures the negative aspect. So with that, what we have, if we want to apply D'Alembert's law, then you have the following statement. You have f of k plus f of b, right, plus f of I minus f of a, the applied force, is equal to 0, right?
Yes.
This is it. So this is how you capture these are the forces that affect the system, and then we represent each one according to the law we use. So for example, for f of k, we use a linear, we use kx. For for f of b, we use bx dot or bx prime. For fi, we use the mass acceleration, and f of a is just the applied force, so we keep it as it is.
So, Doctor, is the internal force same as the applied?
No, it's not. Applied force is, so we use, if applied force is your hand. Imagine that you try to pull the mass by hand. So it's not the same.
Okay.
Is it clear? Any other questions?
David,
Yes.
the force of Fi, why did we do it in the left side?
Okay. Is it acting? Okay. So because, okay, I know that with Newton's law, we say that the sum of all external forces is equal to the mass multiplied by the acceleration, correct?
Yes.
Okay. Now, we just moved it to the other side. It's just what we did here. So instead of saying all external forces is equal to the mass multiplied by the acceleration, we just say that we just move this to the other side and have f of I being equal to minus ma, and that's it.
Mm-hmm.
So we just move it to the other side. So we try to, so in this course, what we do is, because in control, it might make the discussion a little bit easier. What we do is, we just put all the forces acting in the opposite direction in one side and make all the summation equal to 0. And then actually, the next step we do, we usually, this is just a style, you can change this, of course. Instead of having minus fa, we just sum everything that you see, fk plus fb plus fi, and make it equal to fa. So what we do here is, notice the following. We say, okay, we have an applied force to the system. This can be from a controller. This is equal to everything else. So if there is no applied force, then this fa becomes 0, and you have this exact thing. The sum of all fi's is equal to 0. But if you have an applied force, then you put it to the right. Because the applied force is really your input to the system. So we want to see your input to the system. How does it balance the system? I know that mathematically, if you use Newton's second law or D'Alembert's law or whatever I'm just telling you, it's the same. But it's a matter of style that we use in control. It's the standard format that we use in this course. So this is how we represent the system. And it's very easy to see that it is exactly identical to the alternative using Newton's second law or whatever you want to use. You can also say this plus FA. Whatever notation you prefer is accepted. But again, usually in this course, the style we follow, at least in my presentations, is what I just described, that I sum all the forces and then I put the applied force to the right. So to the left, you have everything that relates to the mass, like from the system itself, and to the right, you have whatever you apply to the system. Okay? Any questions?
دكتور
Yes.
FI هي ممانعة الجسم صح؟
Yes, it's the mass multiplied by acceleration.
FI هي ممانعة الجسم، يعني مثلا احنا قاعد نحاول نسحبه بس الجسم لأنه ثقيل، هذا FI صح؟
Yes.
اوكي.
This is really Newton's law. He did not invent it. Because you might have a system that is moving. I mean, if all forces are balanced, still the system can be moving due to Newton's law, right? So it's that force. We want to capture it. And we call it the inertial force here. So inertial is, I think it's mumana, if we want to translate it. Any other questions? Okay. Now we did this, let's say, by a sketch and some little drawings. So let's have it in a more organized way. So we have D'Alembert's law for the mass. We have one mass. So we have one equation and one free body diagram. Okay. And we have the elongation in the spring, X, and the same in the dashpot. Then these are the forces that we have. Only one free body diagram again, because we have one mass. You have force due to spring, Fk, force due to dashpot, Fb, inertial force, Fi. Notice that we have it dotted, so it's not really drawn in the system and like using an idealized element, but it's really important to have it. And D'Alembert's law states that the sum of all forces is equal to 0. Here we have also an external force, the unapplied force, so we put it in the other side. This is it. This is what we have. And again, this external force, later you will see that it can be the control effort. So it becomes, I mean, it might not be important right now for you to put this applied force to on one side and everything else on the other side. But later on in the course, you will see that this gives you a clean relationship and a clean mathematical representation, because once you put an input to the system, you want to study its output, so you can just have all of the dynamics on the left and just the input to the right. It gives you a clean way of manipulating the equations. Any questions so far? This is an important part of this modeling topic. So if you have any questions, please feel free to ask. All right. So what is the procedure for obtaining model of translational mechanical systems? I mean, I stated this multiple times, but let's state it formally. So we use D'Alembert's law to every mass, for every mass and junction point that moves with unknown velocity. We draw the free body diagram. So for every mass, you have an equation using D'Alembert's law. And we show all the external forces and inertial force. Notice, this is the inertial force, Fi. And then use the element laws to express all forces in terms of displacement, velocity, and acceleration. So the inertial force is represented in terms of acceleration. The dashpot B is represented in terms of velocity, the force due to the dashpot. And the force on the displacement due to spring is represented, Fk is represented by, let's say, K delta x. This is K delta x. This is B delta V. And this is minus A minus MA. Okay, so every force, it either relates to displacement or velocity or acceleration, dependent on the force and dependent on the assumptions that we're using in this course. Okay. Any questions?
Here, doctor.
All right. So again, these are the element laws. So for the spring, we use Kx. Fk is Kx, and the direction is to the left. For the dashpot, we use Bv or Bx dot, and the direction is to the left. For the mass, we use Ma, and the direction is to the left. So mx double dot. So this is the relationship of the system. Fk plus Fb plus Fi is equal to Fa. Kx plus Bx plus Mx double dot. The forces on the left equal to the force on the right. So the system is really balanced. Does it make sense? Yes, Abdulillah.
Doctor, if instead of pulling the object, we push it towards the spring, what will change? The, Fk and Fp, right?
Can you change the can you repeat the question again, please? I didn't hear you very
If
well.
we instead of pulling the object, we push it towards the spring.
What do you want to
Okay.
put towards the spring?
Instead of pulling the object to the right, we push it to the left.
Okay.
What will it change? The
So
applied
you have
force will be to the.
a good question. So the applied force will be in the other direction,
Yeah.
and probably the system will move in that direction.
So the same, but will be the everything will be the opposite, right?
Yes, because you will pull the body to the left, and then you will have the spring, and all of these elements will be acting in the opposite direction to your pull.
What about if I?
Okay, Fi is opposite to the applied force using Ampere's law.
Okay.
So it will
Thank
act along the line of the spring and the dash part.
you. Thank you.
No problem. Okay, so you might, so it's like resistance. Like resistance, you might have a serial combination or a parallel combination. For example, if you have two resistances in series in electric circuits, then you add them. If they're in parallel, then you have another relationship that governs the relationship. So here, similarly for mechanical systems, but it's the other way around. So for example, if you have a serial combination of two springs, K1 and K2, then the equivalent spring coefficient is 1 over K equivalent is equal to 1 over K1 plus 1 over K2. So if you want to combine them, then really you have to take the reciprocal of this summation. So give us the following, right? So what is K equivalent? Can somebody give me the answer? What is the equivalent K for the two springs? Yes? Abdulillah?
It will be K1 plus K2 all to the power minus 1, or the reciprocal.
You mean the reciprocal of this guy, right?
Yes.
So it is
دكتور المجموع على المضروب.
المجموع على المضروب. Okay, let's prove it. So we have 1 over K1 plus 1 over K2, the reciprocal of it. So what is that equal to? That inside the parenthesis? You have,
الموضوع المجموع sorry.
yes, okay, so you have K2 plus K1 over K1, K2, and you take the inverse of that, then you have, as you said, K1, K2 over the summation, right? So instead of writing K1 plus K2. I just put the summation sign here. Similarly, for the dash plot, if you have a serial combination, you use a similar formula to capture the new coefficient that governs that serial combination. So K equivalence is the one that can replace the serial combination between K1 and K2. This is K E. Okay. Any questions about this part? Okay. Let's move to the next slide. So we have also parallel combination. For parallel combination, it's pretty easy. You just sum them up. You have K1 plus K2, or B1 plus B2, or if you have even 3 dash pods, you can just add as many as you need. Okay. All right. Now I ask you to grab a piece of paper and try to indicate all of the forces acting on these two bodies. So you have two bodies, two masses. So you will have two free body diagrams, one for each mass, and for every body diagram, show all the forces acting on it with their directions. So let me give you maybe 5 minutes, okay? And ask me anytime if you have any question. And after 5 minutes, we will try to solve it together. So you have until, let's say, 12 p.m. sharp. Is the question clear? Great. All right. Again, usually in my course, I will ask you to solve some examples and exercises to help with the learning process. So please, when you attend my lecture virtually, try to have a piece of paper and a pen, or if you have a tablet or whatever you want to use, in order to try these small exercises in the lecture. Yes, Asil.
Doctor, are the forces of the spring and the dashboard always opposite the direction of the movement?
It depends on the mass.
The direction of the mass of movement?
So it depends. So for the one on the right, for M2, it will be opposite to the direction. But for M1, really, this is the way that M1 is moving. So it will be to the right.
Okay.
So the same force is applied at opposite directions, dependent on the mass you're dealing with.
Okay, thank you.
No problem. If you need more time, please indicate yes in the poll. Otherwise, you can say no. All right, let's have another minute. Okay, so how many free body diagrams do we have here?
Two.
We have two, right? So let's talk about M2 first, maybe. Let me change the color green. I don't like it. So let's use, let's say black. So we have M2, and we have also M1. All right. So we have M2 and M1, right? So what are the forces to the right of M2? So we have FA to the right. Anything else? Okay. No other forces to the right. Okay, what are the forces to the left of M2? What are the forces to the left of M2? All right, FK, FB, FK, FB, FI. Okay. K1, K2, K. Okay. Okay, so some of you, okay, so let's take it one by one. So we have F, K2 from this spring. We have F, B. Do we have a force K1? Sorry. Do we have a force from K1? Acting on M2? Yes, no, yes, no. Okay, I need to hear some answers. So raise your hand and tell me why yes or why no, dependent on your opinion. For those who voted yes, why do you think K1 is acting on it? Okay, seems like the majority is saying no. Actually, the answer is no. The reason the answer is no is this, the force due to K1 is not acting directly on mass 2. It affects mass 2 indirectly because it will affect the displacement x1, and hence it will show up in the dynamics of the second mass, but it will not be worthy of calling it another force acting directly on mass 2. Okay? So we have the third force here is really the inertial force on mass 2. Call it Fi2. Right? Okay. So we stated these forces. Now let's describe them. Let's use D'Alembert's law to express them. So we have an equality here. We have f of a to the right. We have everything else to the left. So what is fk2? It is really k2 x2 minus x1, right? What is fb? It's really b x2 dot minus x1 dot. What is Fi? So I'll put it to the left here. It's really mass 2 x 2 double dot, the acceleration of the body itself. Okay? Any questions about this part? Yes, Muhammad.
Doctor, what about the inertia of the M1?
Okay, the inertia. So when you take the inertial force, you do it for the same body in which you are doing D'Alembert's law for. So you have two body diagrams. For each body diagram, you use D'Alembert's law, and you have a corresponding inertial force. That inertial force is only for that specific mass. M1 is affecting your system, but it's not affecting it in a way that is captured directly here. For example, x1 really is just the displacement of m1. So the inertial force of m1 will affect x1, and hence it will affect the second mass. But we don't express it directly. So this system will be a system of two equations, and that will cover everything for these two masses. But when you use D'Alembert's law, we use the forces that are directly applied to the system, plus the inertial force of the same mass. So you will have another Fi for mass 1. Is it clear?
Yes, clear. Thank you.
Yes, Faisal.
Doctor, what about the force of K1? Because it's affecting M2 in an indirect way, right?
Yes. So we will have another equation for mass 1, and it will have a free body diagram. It has a free body diagram, and we will have another equation. In that equation, we will have K1x1. Okay? So the first equation here is just for the mass 2. Then we need another equation for mass 1.
Okay, makes sense. Yeah.
Okay, good. Speaking of which, let's, okay, somebody has a question. Yes, Ryan.
Doctor, is the string has a weight? Because if we can add the two masses together and make a third equation.
When you want to add the two masses together, you treat them as one body, let's say. I see what you mean. So you may do that, but you need to be careful. Like, but one way that, I mean, there is no unique way of representing the forces in the system. However, the way we are representing here is really a clean way of doing so, and you might avoid possible mistakes. However, because we will have two equations describing the dynamics of this mechanical system, you may manipulate these equations the way you want to manipulate them. It's up to you. So for the spring, we don't consider a mass for the spring. We just have, let's say, the spring affecting the displacement. This is how we deal with it. We don't give it a mass. Okay? Because the spring here is really, we're not looking at just a spring device. It's something we look at as to represent stiffness in the system. Okay?
Clear, thank you.
No problem. All right. So what are the forces that are at M1? So what are the forces to the right? Do I have an applied force on M1? So we have FK2 and FB. Right. So we have FK2 and we have FB. Do we have an applied force here on M1? No, why not? Isn't that moving the body indirectly? Why don't we have it affecting M1? Same case as K1. What do you mean, Mazen? Because it's captured in M2, exactly. So we have two forces to the right. What are the forces to the left? It's indirect, correct, Mazen. So what are the forces to the left here? We have FK1, FI1, FK1, FI1. Excellent. So we have FK1, and we have the inertial force for the first mass, FI1. Okay, let me write all these forces together in D'Alembert's law. So can you tell me what's on the left side and what is on the right? So what is to the left? So what is FK1? All right, we have K1 x1 plus M1 x1 double dot. I mean, again, so let's stick to the same notation in this course. So I'll move these to the left and give them a negative sign, minus K2 x2 minus x1 minus B x2 dot minus x1 dot, this is all equal to 0, right? Because, so we had two forces to the right, FB and FK2, and two forces to the left, FK1 and FI1. So we gave these negative signs and moved them to the left. And then we don't have any direct applied force to this mass. So on the right-hand side, we have 0. But for mass 2, we had FA. Nothing is shown? Okay. So you don't see anything?
We see the screen, but not what you write right now.
So you don't see the second equation?
Yes,
Can't see the second equation.
You can or you cannot?
you cannot.
We can't.
Okay. I don't know what happened. But anyway, actually, we